Welcome back to The Lost Tactician, where history whispers secrets that defy conventional wisdom. Today, we're descending beneath the soil itself to uncover one of Earth's most extraordinary survival stories. Imagine standing before wood that has endured not centuries but millions of years underground, not crumbled to dust, but transformed into something harder than stone. This isn't the result of human engineering. It's Earth's own forgotten formula for ultimate preservation, written in mineral languages we're only now beginning to read. The question that should captivate us is this: how does organic matter, the most vulnerable substance to time's decay, become an object of geological permanence? The answer takes us through soil chemistry, ancient water tables, and the patient alchemy of geological processes. What we discover isn't merely preservation, but active transformation, a molecular substitution so complete that the original wood ceases to exist, replaced entirely by nature's stone-like sentinel. This is the story of mineralization. Beneath our feet, scientists continue to unearth ancient lumber that should have vanished millennia ago. Yet it remains, often appearing pristine, grain still visible, structure intact. Walk through a museum, and you might run your hand across what appears to be wood, only to feel the cold, unyielding hardness of stone. This is the paradox. Wood has become something other than itself. Our intuition tells us wood decay is inevitable. Leave a fallen tree in the forest, and within years fungi begin their work, bacteria swarm through damaged fibers, and gravity reclaims the material to soil. Yet deep underground, in complete darkness, in the absence of breathable air, something entirely different occurs. The rules of decay that govern the surface world hold no dominion here. Instead, a transformation begins, so gradual, so complete, that it fundamentally alters what the wood becomes. This is not merely the absence of decay, it is the active replacement of everything organic with materials belonging to the mineral kingdom. Organic decomposition is an oxygen-dependent process, choreographed by bacteria and fungi that break down cellulose and lignin. But remove the oxygen, bury the timber beneath sediment that seals it from the atmosphere, and the decay machinery shuts down. Anaerobic environments create a biological pause where decomposition slows dramatically. However, anaerobic conditions alone cannot explain the incredible preservation we witness. The real transformation comes from something far more remarkable: water rich with dissolved minerals. Imagine groundwater as a silent architect carrying dissolved elements of stone. Silica from weathered volcanic rock, calcium from limestone, iron oxides from ancient deposits. This water seeps through the porous structure of buried wood, and minerals begin their work of substitution, filling the empty spaces within the wood's cellular matrix, and over vast stretches of time, replacing the very molecules of the original timber with mineral substitutes. The wood becomes something of a hybrid, neither truly wood nor truly stone, but a perfect fossil record of what once lived. The process occurs in two stages. Permineralization, where mineral precipitation fills the wood's empty spaces, adding density and durability. And replacement, where organic material slowly degrades and minerals replace it cell by cell, preserving even microscopic details. A wood cell that once contained living protoplasm becomes a hollow chamber lined with mineral walls. Capillaries that once carried sap become channels of crystallized silica. The entire three-dimensional architecture of the tree is faithfully copied, but the material composition has fundamentally changed. The specific minerals that accomplish this preservation vary depending on geological environment. This variation determines the color, hardness, and durability of the resulting fossil. Silica, in the form of silicon dioxide, is the primary architect in most petrified wood. This element comes from weathered volcanic ash, the breakdown of feldspar-rich rocks, and the dissolution of quartz from surrounding sediments. As silica precipitates and replaces the wood, it forms various mineral polymorphs: opal, chalcedony, and quartz. The silica infill gives petrified wood its characteristic hardness, often exceeding that of the original wood by orders of magnitude. A piece of silicified wood can scratch glass and ring like stone when struck. The stunning colors, brilliant reds, oranges, yellows, and purples, come from trace elements. Iron oxides paint rust reds and deep oranges. Manganese oxides create ethereal blues and purples. These colorations are a geological fingerprint, revealing the chemical composition of the water that brought about the transformation. Calcium carbonate, in the forms of calcite and dolomite, mineralizes wood in marine environments or ancient swamps where limestone-rich groundwater flows. These specimens tend to preserve more original organic material, creating lighter colors and sometimes even the appearance of original grain and bark. Iron sulfides, particularly pyrite, work in oxygen-poor marine sediments where anaerobic bacteria assist. These create specimens with distinctly metallic appearance, gleaming with an almost supernatural luster. What emerges is an object of extraordinary durability, a natural armor so complete and effective that it has preserved wood through epochs of geological change. Density increases dramatically. Mineralized wood can reach densities exceeding 2.5 grams per cubic centimeter, approaching that of stone. This translates to extraordinary mechanical strength, with resistance to physical breakdown, erosion, and weathering that would reduce exposed wood to splinters within decades. Biological immunity becomes absolute. Bacteria and fungi find no purchase in a mineral matrix. There are no organic compounds to consume, no energy sources to exploit. The armor is not merely a barrier. It is an absence of everything that biological decay requires. Chemical resistance emerges from the minerals themselves. Silica is chemically inert under nearly all conditions. It will not dissolve in water, will not oxidize in air. The wood encased in these matrices becomes resistant to leaching, to weathering, to chemical breakdown. Even fire resistance increases. The mineral matrix provides thermal protection, making mineralized wood harder to ignite and slower to burn. Mineralized wood reveals how ancient people selected and worked with timber, the sizes of trees in lost climates, the rate at which forests regenerated. Growth rings preserved in stone provide climate data from thousands of years ago, documenting droughts, abundance, and seasonal patterns that shaped early human history. More provocatively, mineralized wood raises a question reaching toward the future. Can we learn from this process? Can modern materials science replicate the conditions that produce such durable material? Already, researchers explore accelerated mineralization as a means to create sustainable building materials. If we could compress the process of millions of years into time frames measured in months, we could create wood that never rots, that resists fire, that lasts for centuries without degradation. We began with a paradox. How does wood become an object of geological permanence? The answer is profoundly elegant. It requires the right conditions: rapid burial that removes oxygen, the patience of geological time, and mineral-rich groundwater. These ordinary elements, acting across millions of years, produce the extraordinary. The greatest preservation does not come from rigid protection or force, but from fundamental transformation, patient replacement of what is vulnerable with what is durable. In mineralized wood, we see how nature solves the problem of endurance not through prevention of change, but through wise capitulation to it, allowing the very processes that would destroy to become the means of recreation and strengthening. This is Earth's forgotten formula, recorded in stone and mineral for millions of years. As we seek to preserve our own legacies and build structures that endure, we would do well to learn from this geological wisdom. The most enduring things are often those that allow themselves to be transformed. For more insights into how history reveals nature's deepest lessons, subscribe to The Lost Tactician. Like this video, share it, and join us as we uncover the intelligence embedded in the past.